Welcome, dear students, for one more session on problems on IC engines in applied thermodynamics. 17 ME 43, 18 ME 42, BME 401. So we'll continue our sessions and start with the problems on IC engines again. So I read out the first problem. In a trial of a single cylinder two-stroke engine, the following observations were made. The compression ratio is 15, fuel consumption 10.2 kg per hour, calorific value of the fuel is 43,890 kilojoules per kg, air consumption 3.8 kg per minute, speed 1900 rpm, torque on brake drum 186 Newton meter, quantity of cooling water used 15.5 kg per minute, temperature rise of cooling water 36 degrees centigrade, exhaust gas temperature 410 degrees centigrade, room temperature 20 degrees centigrade, specific heat of exhaust gas 1.17 kilojoules per kg Kelvin. Calculate 1. Brake power. 2nd. Brake specific fuel consumption, that is BSFC. 3rd. Brake thermal efficiency. And 4th. Draw heat balance sheet. So now let us write what are the things given in the problem first. So in the problem first he has given us the value of compression ratio RC. RC equal to 15. It is a two-stroke engine. So small n is equal to capital N for a two-stroke engine. Next, then he says it's a single cylinder engine. K is equal to 1. Number of cylinders are 1. Then let us write what are the things given in the problem next. Fuel consumption. He has given us the value of MF. MF fuel consumed is 10.2 kg per hour. So let us convert this kg per hour into kg per second. So divide this 10.2 by 3600. That is, you get answer as 2.833. 2.833 into 10 to the power minus 3 kg per second. So I have converted this 10.2 kg per hour, dividing it by 3600 into kg per second. Then next, calorific value is given. CV is equal to 43,890 kilojoules per kg. Next, after that he has given us the value of air consumption, that is MA. Air consumed MA is equal to 3.8 kg per minute. So divide this by 60 to convert this into kg per second. So we'll take up that later. Then temperature difference, that is rise in temperature, is given to us. Speed is given n equal to, so convert this, that is MA 3.8 kg per minute into kg per second. So you will get the answer as 0.0633 kg per second. Then speed is given n, it is 1900 rpm. Then torque is given to us, T is equal to 186 Newton meter is a torque given to us. Then next, after torque, quantity of cooling water used, that is MW. MW is equal to 15.5 kg per minute. Then next, after that, you have rise in temperature of cooling water, that is, you can call it as T2 minus T1 or delta T. In other words, delta T is equal to rise in cooling water, delta T is equal to 36 degree centigrade. Then after finding out the value of, or after taking delta T, which is given in the problem, next he has given us the temperature of exhaust gas, that is TE. Temperature of exhaust gas TE is 410 degree centigrade. Then room temperature, we call it as TR, that is 20 degree centigrade. Then CP, specific heat of exhaust gas, CPEX is the symbol used. Temperature of exhaust gas is TEX. So it is 1.17 kilojoules per kg Kelvin. Then what all you need to find out? First one is you need to find out the value of BP. Then BSFC. Then next is Bragg thermal efficiency, BTH, and then you need to draw the heat balance sheet. Now let us first find out the value of BP, which is to be found out in the problem. So I will write Bragg power. So we know the equation for Bragg power. BP is equal to 2 pi NT divided by 60 into 1000. I have told you for what reason we are using 1000, to convert watt into kilowatt. So let us substitute all the parameters given in the problem. So 2 into pi into speed is given as 1900 rpm, and torque given to us in the problem is 186 Newton meters. So directly torque value is given to us and speed is given. Speed is given as 1900 rpm, torque is given as 186. So divided by 60 into 1000. So directly we can find out the value of BP. So you get the value of BP as 37.00 kilowatt. So once you find out the value of BP, next we need to find out the value of BSFC. So next find out the value of BSFC. Bragg specific fuel consumption. So what is BSFC? I have defined BSFC as it is the amount of fuel consumed to generate a power of kilowatt per hour. For 1 hour, what is the amount of fuel consumed to generate a power of 1 kilowatt? So into 3600, that is MF divided by BP into 3600, to convert this into per second. So what is the value of MF? It is 2.833 into 10 to the power minus 3 divided by BP value. BP value is 37.00 into 3600. So calculate it. You will get the answer as will be 0.276 kg per kilowatt hour. So per kilowatt hour or per kilowatt for 1 hour, 0.276 kg of fuel is consumed. Next, after this, find out the third parameter, that is Bragg thermal efficiency. Bragg thermal efficiency. The symbol for that is eta BTH. BTH indicates Bragg thermal. For Bragg power, the efficiency of thermal efficiency is based on Bragg power, that is BP divided by MF into CV, and then calculate the value. So multiply this by 100 to get it into terms of percentage, and already I have converted the value of MF in what? Kg per second. So no need of multiplying it by 3600. So 37.00 divided by 2.833 into 10 to the power minus 3, which is the value of MF, into CV value. Into CV value is 43. I think it is 43,890 into 100, which will fetch me the value of Bragg thermal efficiency as 29.75%, or if you have not used percentage, then you will get the answer as 0.2975. I repeat, if you have not used 100% here, you will get the answer in terms of 0.2975, and if you have used multiply it by 100, you will get the answer in terms of 29.75. Then after getting this value, then let us take the fourth part in the problem. that is to find out the value of, or to draw heat balance sheet which is asked in the problem. So heat balance sheet, heat balance sheet. So first we need to find out the energy supplied. So, or heat supplied by the fuel. So heat supplied by the fuel is mass of the fuel multiplied by calorific value of the fuel. So mass of the fuel is 2.833 into 10 to the power minus 3, which you have converted that mass of kg per hour into kg per second into the calorific value. That is, the calorific value is 43,890 multiplied by 60 to convert this into what? Per minute basis. Otherwise, the answer what you get will be in terms of kilojoules per second. I want the answer in terms of kilojoules per minute. And once you get the answer in terms of kilojoules per second, it is kilowatt. So usually the heat balance sheet is plotted in terms of minute basis. So it is kilojoules per minute basis. So therefore it is multiplied by 60 here. So you got the answer to be as 77,460.42 kilojoules per minute. This is the value of heat supplied. Then next we will find out heat equivalent to BP. So B, heat equivalent to BP, heat equivalent to BP, that is brake power. So it is nothing but BP multiply it by 60. So you have got the value of BP as 37.00 multiply it by 60. So you get the answer to be as 2220 kilojoules per minute. Then after this, find out heat carried away by cooling water. So heat carried away by cooling water will be equal to mass of cooling water, that is mW, into Cp of cooling water into T2 minus T1, that is rise in temperature of cooling water. So mass of cooling water given to us in the problem is 15.5. It is per minute. So let us not change that value. So 15.5 Cp value you know, that is for water it is 4.2. Then into change in temperature, that is T2 minus T1 is 36. So you will get the answer to be as 2343.6 kilojoules per minute. So once you get the value of heat carried away by cooling water, next find out heat taken away by exhaust gas, or heat carried away or heat taken away by exhaust gas, or heat loss to exhaust gas, all meaning the same. I repeat, heat loss to exhaust gas or heat taken away by exhaust gas or heat carried away by exhaust gas all mean the same. So what is that equation? It is mass of exhaust gas into Cp of exhaust gas into temperature of exhaust gas minus room temperature. So mass of exhaust gas is known to us, right? That is mass of exhaust gas. If you want to find out, first you have to find out mass of air, mass of fuel plus mass of air is nothing but mass of exhaust gas. That is the mass of fuel and air which is burnt inside the engine gives me what is combustion products or exhaust gas. So what is the mass of exhaust gas? That is mass of exhaust gas will be mass of fuel. So mass of fuel plus mass of air burnt. So mass of air burnt, that is mass of fuel, is 2.833 into 10 to the power minus 3 plus the mass of air burnt is 0.0633 into Cp of exhaust gas, that is 1.17 into temperature of exhaust gas, it is 410 minus 20. Please note here, I am not converting both the values of temperature in Kelvin. If I convert also, it is a difference, so therefore it remains the same. So therefore 410 plus 273 minus of 20 plus 273, 273, it is a subtraction, so it gets subtracted, so therefore I have not converted that into absolute temperature. So what do I get? I get the heat carried away by exhaust gas as 1810.59 kilojoules per minute. So once I get this value, right, let me find out the last one, that is unaccounted heat loss. Unaccounted heat loss. This unaccounted heat loss is nothing but the heat lost due to friction, or it may be due to radiation, right? So it is nothing but heat supplied, that is you have found out the value as 7460.42 minus of heat carried away, heat equivalent to BP, that is 2220 plus heat carried away by cooling water, that is 2343.6 plus heat taken away by exhaust gas. If you add them, right, and get it subtracted from 7460, which is nothing but heat supplied, you will get the value of unaccounted heat loss, that is it is 1086.23 kilojoules per minute. So once you find out this value, right, next is you have to plot a table in terms of percentage basis. So to plot this table on percentage basis, what I will do is, with the values whatever I have found out, with the red pen I will write the percentage, that is heat equivalent to BP, whatever I have got, right, divide this by 7460, which is nothing but heat supplied, you will get in terms of percentage, that is it is 29.76%. Next, heat carried away by cooling water, right, it is 31.41%. Then next, heat taken away by exhaust gas. Heat taken away by exhaust gas is 24.27%. And then the last one, unaccounted heat loss is 14.56%. So with all these four values, right, in terms of percentage, right, if you express this in a tabular form, right, it is nothing but your heat balance sheet. So what are the parameters there? Serial number, you can write particulars, then heat in kilojoules per minute, and then here in terms of percentage. So serial 1, heat supplied is 7460.42, which is nothing but 100%. Next, heat equivalent to BP, so that is heat taken away by BP, it is 2220.00, which I have told you is about 29.76%. Next, heat carried away by cooling water. Heat carried away by cooling water is 2343.60, which is 31.41%. Next, heat lost to exhaust gas. What is that heat loss to exhaust gas? It is 1810.59 kilojoules per minute. It is 24.27%. 0.27%, and the last one is unaccounted heat loss. Unaccounted heat loss, which is nothing but 1086.23 kilojoules per minute, which is 14.56%. So if you see totally, right, that is all these together, that is heat equivalent to BP, heat carried away by cooling water, and heat loss to exhaust gas, and unaccounted heat loss should be, right, if I add these values or in terms of kilojoules per minute, it should be equal to 7460.42, and the percentage whatever I've shown on the right side should be equal to 100%. This is the problem what we have solved for today's session. Thank you.